Okay, excellent. You getting it? Oh, no, let's see. Oh, yeah, that's the solution. Okay, so this one here sees fully the one charge. It sees fully the one charge. This one is a two charge. It's blocked by one, and this is far out already. It's further away. It's in the 3p, not in the 2p. So this one would be easier. This one would be easier to remove than this one. But this one here is 3 blocked by 2, and this is even further out, so it barely sees that charge, the nuclear charge. With this would be, the effective is essentially 1. The effective charge is 1, because this is blocked. One charge is blocked by this, so it sees one charge. Two charges are blocked by this, so it sees also one charge, but it's far out, and this is one charge, and there's no blocking, okay? So this minus 1/9 R and 1/16, you can know this by, if I give you the set efficiency, then the efficient charge, then you would know that. But you just can deduce it from thinking about the blocking, okay? So the right answer was this. So, now we need to come to something else. Really something else. We know 3 quantum numbers so far, and with this we can place 1 electron. But there's a 4th quantum number, and it's called the magnetic quantum number. It's M sub s. The magnetic quantum number is M sub s. So these electrons, they have a negative charge, and they travel in a waveform, okay? And so they act like little magnets. So if you have a, not a quantum magnet, if you have a regular magnet, so there's the north here and the south here, and you have another magnet north, south here, and you don't bring them too close to each other, you move this one, the other one moves too. You move it all the way, it moves all the way. You move it this way, it moves this way, okay? Can do this with iron filings, iron becomes magnetic and does all these wonderful figures, okay? So this would be classical mechanics, classical physics. So if you shoot them through regular magnets, if you shoot little magnets through a magnetic field, you get something like this, a classical behavior. There's, most of them go in the middle, some of them go in the side, some of them, because the north and the north repulses and the south repulses, they go straight to the middle, repulsion is the least. So you get, this is the distribution, this is intensity, yeah? Okay? They hit the wall here, of course, yeah? Okay, intensity and wavelengths, is that related somehow? Intensity and wavelengths? No, not related, okay? Intensity is just a lot of them, okay? That's all. Okay, I think remember that. All right. So, but these electrons, we know they are quantum particles, they have a quantized spin. They can have only 2 states. One state up, and one state down. State up, state down. Spin up, spin down, spin up, spin down. They don't go like this. They go spin up or spin down. So that quantum number, we call the spin quantum number, and it could be spin up, then they have spin, and they are half integers. It's 1/2, plus 1/2, and minus 1/2. Or spin down, we say that's down, we put a minus in. It doesn't matter if it's up or down, okay? It's the same energy state, essentially, if they're by themselves. But if they're not by themselves, then it's a different energy state, and this is what we're going to allude to in a minute. So we have now 4 quantum numbers. There's the quantum number spin up and spin down. And with this now, we have n, L, m sub L, and now we know that they also have a spin. They can have up or down, so they can occupy this orbital in either state. That means we can bring 2 in one orbital. And there's now the Pauli exclusion principle says that no 2 electrons can have the same set of quantum numbers. So if you have a set of n, L, m sub L, the same, this would be, let's see, a 2p. Okay, you have 3 2p's. But you can only have 1 electron with an up state in there, or 1 with a down state. That means that m sub s has to be different if these are the same. And this is an orbital, that's how we describe the orbital. So you put then the electrons in there, and you can only put 2 electrons per orbital, 1 with up state and 1 with down state. And so this one, if we have, and this is theoretical, if you have 2 orbitals, doesn't matter, 1, 2 orbitals. So if you put this up and this down in the same orbital, that's not right, okay? So this is against the Pauli principle. So if you have this one up and this one down, this is one orbital and the other orbital, they have the same energy. This is also a high energy. That's the highest energy state, that's a high energy state. And the lowest energy state is, first you have them parallel, either all up or either all down, it doesn't matter, yeah? As long as you follow the rule. And so that means the Hund's rule, Hunt means dog, not dog the bounty hunter, but that are degenerate orbitals. If you have p orbitals, px, py, pc, they have the same energy. Okay? They always will have the same energy. The 3p will have a different energy than the 2p, but they have the same energy. And the d orbitals sort of have always also the same energy. We call them degenerate. Okay? So you fill them with parallel spin. So you have p orbitals, for example, you first one up, then the next one up, and the next one up. And then you go down, down, down. Okay? Now, so we can be, you and I, we can be in the same chair. Okay? You get up and I sit down, and then I sit down and you get up, and vice versa. So we can share the chair, actually. But we can't be in the same state. Okay? When I'm up, when you are down, when you are sitting, and vice versa. Okay? So we can share this orbital. That's the first quantum number. Now, imagine you're sitting in a bus. Just you and the driver. And the bus has 2 rows, all the way to the back, all the way to the back there. And there you sit. First one in the front pair, and you sit by the window, you want to look out. In comes somebody, and sits right next to you. This would be absolutely weird, okay? Would freak you out. What is going on here? You know, the whole bus is empty. So what happens usually? The next guy comes, he sits alone in his row, the next guy, the next guy, the next guy, the next guy, the next guy. So till all the double seats are filled with one person. And then the next person sits next to another person, and this doesn't feel weird at all anymore, okay? And so this is how this works with electrons. We build up first where they have the same energy level. We put, see, with the same spin first, the electrons in the same energy level, and then we put the opposite spin as the second seat. Did you get that? Okay, don't get freaked out. Now, so this one is not, so we start this is what we're doing. We're filling the bus that way, okay? Ever happened to you that the bus completely empty, and the guy sits right next to you? So these behave like fermions. Fermions, these are, they can only, in a certain lowest energy level, there can be only one in the same energy state where it has to spin down, okay? This is protons and neutrons and electrons, they behave like fermions. But there are certain atoms, they behave like bosons. And not bosons, bosons. There was a now famous, I think he was a physicist, an Indian physicist, Bose was his name. I don't know if he's related to the stereo stuff, but he sent a paper to Einstein in 1925. And he said, you know, can you review that paper for me? And Einstein, it was written in English. At the time, the language of publication was German. So he had to translate everything into German and publish in a German journal, okay, especially the quantum mechanics. So Einstein read this paper and he wrote it back and said, it's a great paper, I don't understand it, but there's nothing wrong mathematically. It must happen. And so then he translated it into German and published it together with Einstein, and it's the Bose-Einstein relationship then. And people actually got the Nobel Prize in 2001 for this. This was two guys from the University of Colorado. The name was Cornell and Wieman, and the third guy is from MIT. And this is a German by the name of Ketterle. And he thought, you think I have a heavy accent? So this guy, by accident, I walked into a broadcast. It's called Deutsche Welle. They do a broadcast in English. And I walked into and they're interviewing this guy. I said, Bose-Einstein, I'm going to talk to more about this. I listened to this guy Ketterle, and so I have a perfect non-accent compared to this guy. All right. Anyhow, so what these guys did, when you cool, for example, helium-4, you can cool this so low in a state that you can get all the helium atoms in the same quantum state. So they behave like bosons and not like fermions, which electrons don't do that. And so they could, for example, they did rubidium. Rubidium atoms, they cooled down to 170 nanokelvin, and then investigated this, and they see they're all in the same energy state. That's the Bose-Einstein condensate, okay? So just for you at the sideline, we're the physicist here? Physicist? Okay, you ever heard of it? Yeah? Did I say it right? Okay, good. I'm a chemist only. So no, we do a lot of physics. And so just as a sign, so they have integer spin, fully integer spin, and they are all in the same state. Of course, electrons don't do that. And when we talk about now the electrons, we're going to build up now. It's called the build-up principle, or the German word Aufbau principle. So now we're going to assign, we go through the periodic table and assign electrons to the individual orbitals. So we start with n equals 1, okay? N equals 1, there's the 1s orbital, hydrogen. It's a 1s, it's an unpaired electron. Unpaired electron, they are magnetic, they have a spin, okay? And if the next one would be, now I can put a second electron in the same orbital because I can put the opposite spin in there. That's allowed. They don't, not all four have the same quantum number. One quantum number is different. That's the m sub s quantum number. So I put a down spin, so I call this a 1s2 configuration. So helium is a 1s2, and with this there's no magnetism. It cancels each other, no magnetism. Now I go to the next period, you see, there's a period here. That's helium, that's a stable configuration. Now n equals 2, I start again. N equals 2, I have the 2 electrons already in the 1s state, and now I go to the 2s state, the next higher state. So I need the third electron I put in the 2s1, so I have the state 1s2, 2s1, that's the ground state for lithium. This is magnetic, you see here, unpaired electron. Beryllium, element number 4, has 4 electrons, so it's a 1s2, and I put another one in here, it's a 2s2, okay? And now, of course, no unpaired electrons, not magnetic. Now go to boron, not boron, boron, okay? Boron, it's a 1s2, a 2s2, and now what's the next quantum number? L equals 1. Now we go to P, 2p. To P or not to P? What did I just say? To be or not to be, that's what it means, okay? So I'm going to be thrown off the college here, probably. So 2p1, okay, terrible. 2p1 it's Monday. It's magnetic, okay? Now we go, carbon has 6 electrons. It's a 1s2, 2s2, 2p2, okay? And there, you see, we fill, with the same spin orientation, we fill the second p orbital, will be magnetic. It's very magnetic, because it has 2 unpaired electrons. Now we go to nitrogen. Nitrogen is element number 7. We have 2, 4, 6, 7 electrons. So the last one, we fill in the third free p orbital. Okay, that's even more magnetic, because you have 3 unpaired electrons than this one. Now we go to oxygen, and oxygen has 8, 2, 4, 6. So we now have to populate, use the second, the p orbital before the second. We have to put 2 in the p orbital, so upspin and downspin. So it's a 1s2, 2s2, 2p4, less magnetic than this, about same magnetic than this here. Now we go to fluorine. Fluorine is element number 9. We have a 1s2, 2s2, 2p5. We have to put the p, fill this here with downspin, magnetic still. And now we get to neon. That's the end of that period. Neon has 10 electrons. And 1s2, 2s2, 2p6. So we fill that one in here, 2p6. Not magnetic. Very stable configuration. Now we go to the next period. So all the 1s, 2s, and 2p's are filled. For sodium. Sodium, we need to go now a 3s1 and fill this with 1. So but we also can say, this is the neon configuration. We put neon in square brackets. And so, this is the 3s1 and neon configuration and 3s1. That way we don't have to write this always. And this would be magnetic. Now, let me ask you. If you flip an electron, if you're all in the same spin, that's a... why don't you think about it? When an electron spin flips, but which of the following is the energy not altered? So we have a nitrogen, and I give you that table here. Get thrown off the stool here. Okay, we have nitrogen and oxygen and fluorine. Nitrogen and oxygen and fluorine. So if I take this, flip this, I flip this, I have a different energy situation. And if I flip this, do I have a different energy situation? That's the question. For which of the following is the energy not altered? Nitrogen, oxygen, or fluorine? Think about it. I forgot this. Okay, let's have a look. Yeah, that's pretty good. You recognize that, let's see, you recognize, I don't know how to push this thing here. You recognize that if I have this situation here, that is an unallowed situation if I flip this, so that would be a high energy state. Okay, you have to fill the first parallel. If you flip this, that would be an unallowed energy state. The same as here. But this one, it really doesn't matter if you put it upspin or downspin, it's the same energy. It's not a different energy. So fluorine is could be up or down, and this was the answer. Now I'd like to say something, if you put the camera please on me. These fermi ions, electrons, they have this very funny symmetry. If I stand like this and I turn like 360 degrees, I have just the same symmetry again. So if you have a fermi ion, it's an electron, for example, that moves on a Möbius strip. You see, it's red here and it's green here just for you to see it. So I go 360 degrees around, and it doesn't have the same orientation. You see that? It's a difference. So I have to go 720 degrees around, and then it has the same orientation again. So it has a very different symmetry, these fermi ions. Okay, fermions. With this, good luck tonight, and I see you on Wednesday.